call. Hello everyone, very nice to see you today. Hope your travels were safe to Bangkok. So I'm Sasha from Risk Zero, and let me just adjust this a little bit. I'm freakishly tall, so okay. So today I'm going to be talking about Steel, which is our Ethereum library for the zkVM. If you're familiar with the zkVM, that's great, but if you're not, don't worry, I'll run through the basics for you as we go forward. So I guess Steel is nice. We have a lot of metal metaphors with Rust and Foundry and Alloy and all these other ones. So Steel is from Risk Zero. It's an Ethereum library for the zkVM. So that's all great, but what does it actually unlock? And then we'll talk about how it actually works. So here's an example that Eigenlayer uses Steel, or how they use Steel. Specifically, they have a metric ton worth of view calls and SLOs they want to carry out. It's physically impossible to carry these all out in one transaction. In fact, they want to compress 40 blocks of execution into one transaction, which costs around 1.2 billion gas. That's not possible, and so we worked with the team for a while, and they've started using our Steel library. So Steel here, for about $10 to generate the proof, they've run 40 blocks worth of execution, and it costs around $10 on L1 to actually verify the proof. Now, of course, there's a trade-off. There's latency, right? So to generate the proof, there's latency. But in fact, for Eigenlayer's use case, that's fine. But bear that in mind if you're thinking about using Steel. But we'll go through the trade-offs as we go forward further in the presentation. Actually, 1.2 billion is, actually gas is pretty low on the execution front. Like computers are super quick compared to the EVM. And so you could run much more execution. And this is the topic we talk about with Boundless execution. Boundless is a product from Risk Zero, and here we're talking about we're going to have a decentralized proving marketplace, but here we're talking about Boundless execution using Steel, because Steel will be part of that as well. So what does it unlock? Well, unlimited execution at a constant gas cost. The constant gas cost is just the gas cost of the verification of the proof. And the price of execution proving is just exponentially going down. It's a tiny fraction of the price of on-chain execution. And the price has just been going down and down since Risk Zero zkVM, so the price of proving is just getting lower and lower. So I've said a lot of reasons of why to use Steel, in the sense of you have a large execution you want to carry out, but you can't carry it out without paying a very large amount of money for the gas. So what is Steel? You can think of it as smart contract execution proofs, and we can break that up a little bit. So first we can do smart contract execution, and then we can have proofs. I won't bore you too much because I'm sure everyone knows what smart contract execution is, but some famous examples. You want to swap something, you got to do some execution based on checking the balances and making sure that everything's legit, and actually carrying out the swap by updating the balances, right? So usually you have some sort of state you want to change and carry out some calculation against. Same with adding liquidity. These are from Uniswap v2. So a usual workflow in smart contract execution, and I appreciate this is a little hand wavy, but it helps to explain Steel, is we have an input, which is a transaction. That transaction is basically requesting a state update from the inputs, the arguments. You can kind of think of a smart contract as having some sort of rules for the logic and also pointers to the state. And then we can kind of think of the EVM as the VM, the stack, and it's going to go through and do the instructions and actually get to that state update. So that's great. Good question is that when you start taking execution off-chain, it becomes a bit of a problem, because the whole point that the state on-chain is for it to be verifiable. Now, what do I mean by verifiable? I mean, if we want to execute on X and X is 6, we would like there to be a consensus that X is 6, because if we take it off-chain and it's 12 all of a sudden, then our execution isn't valid. So blockchains are fantastic at this. Execution needs to be verifiable. There's a whole consensus and everything like that to make sure that the state in each smart contract is valid at the point in time. So we need to keep that in our workflow as we go off-chain. So that needs to stay. And smart contract execution is limited. The EVM gas is expensive. Layer 2's help, but the execution is still pretty limited for more modern use cases. So we've gone through smart contract execution. Let's have a look at what proofs. The zkVM is very straightforward. If you've ever run any zk things before, you may have used a domain-specific language, written circuits yourself. In the zkVM, you don't have to worry about any of that. We handle that for you. You just write some Rust code. It compiles to a RISC-V target, and then we handle that with a big RISC-V circuit and generate a proof for you. So usually in a VM, you have a program, some inputs, and you get an output. The only difference with a zkVM is that you still have a program, inputs. We call those a guest program, this VM terminology. You get an output, but you also get a proof that that program ran in the right way, and it can be a Stark or a Snark. So we have some terminology here. We have guest code, which we call the guest program. So actually it compiles to an ELF binary targeting RISC-V, and that's why we get the name RISC-0 from. And we have the ZKVM that you pass it through, and you get what's called a receipt. Don't worry about that, I'll explain that a little later. So you can think of Steal as smart contract execution proofs. So actually, before we saw we had Rust code through the ZKVM, Steal allows you to write some Solidity code in the ZKVM and compile that and execute against that. So before we saw this workflow where we had an input for transaction and we're asking for a state update based on some rules in a smart contract. Now with Steal, it's a little bit different because we have some Steal code in the ZKVM and that's actually carrying out some execution. And basically the input transaction and the EVM here are always doing the same thing when you use Steal. They're going to send through the proof in the call data and we're going to verify the proof on chain. That's pretty much all the EVM is handling and some state updates. So then you can think about the smart contract as keeping the state, and the logic will be off-chain using Steal. So how does that work exactly? A good question. So a fundamental operation in Solidity is a view call. So when you check, for example, a balance here on ERC20 contract, very straightforward, I want a balance of something in order to make sure it's legit. So we use Alloy in the ZKVM, so Alloy is a Rust library, and for Solidity, but basically giving Rust bindings. So here, you just write in a handy sol macro they have, you can write any Solidity in there. Here's an interface that declares a function signature of a view call that we want to carry out in the guest program within the ZKVM. So here we're just going to check some balance. So here we have the Solidity code at the top, and we have what's called a guest program. Now, if you've used the ZKVM before, it's very familiar, but let's walk through it. So we have a call there with balance of call, and in the returns object, we're actually instantiating a contract, and we're passing through this EVM environment on the returns line. And then we just have this assert line here, which says, hey, if the balance is bigger than 1, then this proof will basically be valid and this guest program will run. And then we have some boilerplate in the bottom that I'll get to. Now this isn't particularly exciting, because all we've done here is call a contract view call, instantiate it, and then check the balance, make sure it's larger than 1. For the example for this workshop, it's just a stupid example, but in general, what is actually exciting is if you've used the ZKVM before, there's a couple of things you have to ask. The first question is, the ZKVM guest program has no network access. It's usually the guest program is, entirely, it is a pure computation. You cannot, there's no file system, there's no way to access the network. So how am I calling an RPC? Because evidently I need to in order to get this balance. So that's a good question. And another question you could ask is, how can I trust this view call data within the ZKVM, right? Like, maybe there's a malicious RPC, or maybe it's out of date or something, or stale. A couple of questions that are very worth asking here. Now, thankfully, Steal fixes most of these things for you in the background, and that's what we're trying to do with abstracting these away for you, so you don't have to handwrite these like storage proofs all by yourself. So we use RAVM within the guest program. When you write Steal, when you instantiate Steal, all of this is handled for you. So you don't have to worry about it, so I'll show you how that works. So there's a host and a guest. So we've seen the guest program, that was this one, where, hey, I want to do something, and based on that, I want to do something. Like some execution based on some smart contract state. We'll get to how it's verifiable in a moment. Now, that's handy because on chain, we usually have a view call and then do some execution based on it or something rather like that. So we want to carry that out in the guest program. That's great. As I mentioned, the guest program has no network access. So what we do is we have a host program. The host program is another file in your workspace, in your Cargo workspace, and that one does have network access and can set up what's called an EVM environment, or we call it for Steal. So it's actually going to talk to the RPC, and usually the host program is in charge of passing inputs to the guest program, maybe getting the outputs from the guest program and doing something with them. You can kind of think of it as like a script wrapper on the guest program. Now in this case, it's going to actually call the RPC and get the data. Now it's great to just call the RPC the balance and say it's 10 and give it to the guest. That's fine. But that's not enough because we can't trust that necessarily, especially with this, like, what chain is we getting it from? We have to match a lot of things here. So we also ask for the Merkle proof, the Merkle storage proof from the RPC, and obviously block metadata, so to match that against, so usually the block hash. And we pass that through to the guest program, and in the guest program, when you saw this code, you didn't have to do any of the Merkle proof verification. This is all handled for you when you just instantiate the contract and do the calls. But what's actually happening is that it's verifying the Merkle storage proof within the guest program. And remember, the guest program is the one that's being proven. So if it verifies, you also have a proof that this view call data matches the block hash that the RPC gave you, which is great, but not enough yet. And then you do some execution on it, and you get a receipt, right? So now we have some sort of at least a little bit more verifiable state than we had before. And a host program is very straightforward. We have a provider, RPC URL, all used to that, and we build this environment. And this environment in this specific case has a specific type, which is the ETH EVM environment. Next up is a very important line, is this pre-flight line. And pre-flight is the one doing the collecting the RPC data to build the EVM environment. And this line will handle and mute the environment here to give it all the required data, including the Merkle storage proof for the guest. So now the guest has a way of basically verifying that the view call data matches to at least the block hash it was given. And also in the guest, this is the full guest program now, so it's not too long. You can see that we've read the input at the top. We've got contract and account, which is useful because we want to know what account we want to check against in the token contract. And the input is just smart enough to read based on the types, so you can just write env.read and it'll read the input from the host to the guest. And we've seen this before, and we're going to do some committing at the end, which is also important, which we'll get to in a second. So, thinking about the pseudocode for a Steal contract, a smart contract that uses Steal, we're going to do something, and we're going to pass through what's called the journal data, which is the outputs of the guest program, and the proof. And we're going to validate the journal, and we're going to validate the Steal commitment. Now, that will get into that in a second. The meat of this is we're going to verify the proof that this guest program executed this logic off-chain based on some verifiable view call state. And then you can do something else after. The do something else is almost always going to be update the state based on what the proof wants. Because at the end of the day, you want to take logic off-chain, and then what you want to use the on-chain version for state that is under consensus. So what does this look like on-chain? Without Steal, you can see a contract here as an example that checks a balance, and if it's bigger than 1, as we've seen, we're now going to increment a counter. So that's the state update I mentioned. Now with Steal, I appreciate that it looks much more complicated, and it probably is, but this is the same every time you do, no matter what execution. So if this was much more complicated, it would still look like this, and your execution would be offloaded to the Rust file as opposed to in Solidity. So here, there's a couple of steps. And there's this thing called a journal, which is what the guest program writes to. You can think of it as a journal. The guest program writes outputs to it. You write your public outputs to it, and you can write anything else to it. We're verifying that. That's fine. But what's important here is that require steal.validate commitment line, which we'll get to in a second. And then we're just going to verify the proof. And only if the proof is verified, we're going to get the counter to increase. And remember, this is basically the execution we have, the guest program. Skip forward that. So Steal commitments are very important. So if you remember, we now have a guest program that has some verifiably-ish state. It has a Merkle proof that it's proven, and it has that against the block hash from an RPC. But when we're on chain, we don't actually know if that block hash is valid or if that state existed at the block. So in Steal, when you request the information from the host, it usually just goes to the latest block, but you can pin a specific block. So in this bit at the end here, we saw this thing called a commitment that was written to the journal. And this is boilerplate from Steal and into commitment. You'll always see that when you're using Steal. And Steal retrieves view call state at a specific block, and you can pin it if you want. And so you can say, I want block X. The relevant block data is committed to the journal for validation on chain, so that the journal will contain that commitment we call, which is just a struct. And that's Steal's trust anchor, is the block hash. Now, actually, what's actually happening on chain, we're using the Steal library. So you saw that steal.validate commitment. That can be we have templates for that. You can they'll link into your compiler and Sol C, and you can deploy those. But what actually is happening when you're validating a Steal commitment is you're validating the block hash from the context of on chain. So basically, we have a block hash, and we made sure that the view call state matches to the block hash with that Merkle storage proof. But we don't know on chain if that block hash ever existed or if there was consensus around that block. So what we're going to do is we're going to use the global variable from Solidity block.hash and actually match against that. And only if they match can we verify the proof that, okay, this information has this information that we pulled from a view call state did in fact live on chain. So in fact, this proof is valid. That view call state was at block X, and we're ready to rock and roll with the state update based on the proof verification of the smart contract execution proof. Now, one thing here is, of course, block.hash, the global solidity variable block, only has context for the last 256 blocks. So you have about a 50-minute window before your execution proof becomes invalid. That's in most cases reasonable, but it's not ideal. So there are ways of, if you're on Optimism or an L1, there are ways to access the beacon chain, which is after the merge, where it has a block root information, which stores the block header for around 24 hours. There are actually ways of doing this where you like bookmark and pin the block, and we're actually adding that to Steel, but for the purposes of this, we'll leave it there. So 50 minutes and 24 hours, depending on the chain you're using. So to summarize, we need smart contract execution to be verifiable. We know it's very limited. And we know that Steel allows us to do execution proofs within the ZKVM. Remember, the ZKVM has no network access, so Steel manages this all and abstracts it all the way for the developer like yourselves. Steel uses REVM to use like minimal EVM environment that can make sure to verify everything and do the calls against. And we pre-flight all that data and check the numerical proof within the guest. And the execution proof can be verified on chain without also those commitments that's validated. So that's everything from me today. So that's Steel. So thank you very much for listening.
Thank you very much, Sasha. Big applause to Sasha, please.